Hello everyone, welcome to solving session. My name is Shaban Mchomv, and today we are going to see a question on the topic of complex number, particularly advanced mathematics paper 2. And now let's see a question that appeared in this advanced mathematics paper 2 in the year 2024. So the question contains 4 parts, A, B, C, and D. And now let's start with case A. How do we solve that part A? So case A, we are provided with a condition that if 3m plus 10ni plus 5n equals to 13 plus 20i, where m and n, these are the members of a real number, belongs to real numbers, and the I square equals to -1. So here, I, we know it's a part of a complex number. That then is imaginary part of a complex number. So here we are given already that I square equals to -1, that we are required to calculate the value of these constant m and n, which belong to the set of 4 real numbers. Now, if that to be the case, now we can solve and start. So here, what is needed? Values of m and n. These are what are needed from this problem. So from this equation now, whereby here it means we compare two complex numbers. If we just compare two complex numbers, now we can compare the separate part, like the real part will be the same. For example, 13 will be equal to 3m plus 5n. And that 10ni will be equal to 20i, because the two complex numbers are compared. So from left-hand side and right-hand side, we only compare the imaginary and we only compare the real parts. So if that to be the case, now we can write 3m. If we plus 10ni, then now we plus 5n. This is less more to 13 plus 20i. So here now we can arrange 3m plus 5n, that's the real part. Then now plus 10ni, that is also imaginary. Now equals to the real part plus 20i, imaginary part. Now because the two are complex number, now we compare. So we equate real part of this side equals to 13. So that's equation 1. Then again 10ni equals to 20i. So I and I now, if we divide now, will cancel out, and we end up getting, it will be now 10n equals to 20. So this now will represent equation 2. Now, if we are going to solve by the substitution method, if we solve algebraically, 3m plus 5n equals to 13 as equation 1, and 10n equals to 20 as equation 2, now we end up getting, so we say on solving algebraically, we have, what exactly do we have? So here is 3m plus 5n equals to 13. And now if we divide by 10 both sides, we end up getting n equals to 2. So if we apply substitution where n now here in equation 1, if we substitute 2 where n, so we'll end up getting 3m now plus 5 times 2 is less more to 13. So this much becomes 3m. Here it is 10, because 5 times 2 we know it is 10, equals to 13. So 3m now equals to, now we collect the like tens. So these numerical terms has to follow the other numerical term to the other side. So it will be 13. So if it goes, now we subtract. So we end up getting 3m equals to 3. Because 13 minus 10, we get 3. So I need m. So what next? It means we need to divide both sides by that coefficient 3. So we divide by 3 by 3. So m, we end up getting 1. So now we say m equals to 1, and our n equals to, our n was 2. So up to that point, we have managed to find the values for m and n. how we equate the complex number to the right and to the left side through the real part and the imaginary part. Then what goes was the solving algebraical of the two equations that we generated, and up to this point we have the values for m, which is 1, and n, which is 2. So that is the story of part A. Now let's see how we can solve part B. Case B. Now case B, we are required to use the Moivre theorem to prove that this is the multiple angle for the tangent function. The multiple angle for the tangent function, that is tan of 4 theta equals to 4 tan theta minus 4 tan cubic of theta over 1 minus 6 tan square of theta plus tan, this is quadratic now. This is tan of theta raised to exponent 4. So it means the Moivre theorem, always we can apply. One of the application of the Moivre theorem in complex number is to change multiple angle to powered angle, or powered angle to multiple angle, and even sometimes it can help us to find the roots or the values for the complex numbers when the function equals to 0. So among the application here, it means that we are going to use the Moivre theorem. We need to change this multiple angle. You can see 4 theta, that is multiple angle. How is it going to appear in the powered angles? You can see here power 3, power 4 here, 2 square. So the Moivre theorem. So from there now, so we can say now using, the concept is using the Moivre theorem. The Moivre theorem to express multiple angles, multiple angle now to powered angle, to the powered angles, to the powered angles. So that's the key idea of that question. Now, as usual, if you are told to prove it, means now we need to use one side. But for here, let's refer the Moivre theorem. That's the Moivre theorem. Now from the de Moivre theorem, now it states the cosine of theta plus I sine of theta. This is complex number in polar form. That you can see the angles and the radius, or yes, the radius. But here we just use, we assume the value of r, or the magnitude, or the modulus is 1 unit. So we can just say this complex number expressed in polar form has magnitude of 1. So it's like saying now cos of theta plus I sine of theta. This is I, the imaginary parts of this complex number. Now, if raised to n, this is less more to say the cosine of the multiple angle now will be n theta with plus I sine of n theta. So it is going to be like that. So that's the concept of the Moivre theory. Here, provided r equals to 1 unit, it means r we normally note in complex number as modulus of the complex number. And this theta here, we normally consider it as argument of that complex number, the angle. So, if that to be the case, there from the problem, n equals to 4, as you can see here, and it is 4. So if we try to plug in into the polar form of a complex number by the Moivre theorem, this becomes, now it becomes here raised to 4 equals to the cosine of 4 theta. Now we plus I sine of 4 theta. So if that to be the case, then now there we have tan, and here we don't have tan. We have only sine and cosine functions. Now, if we can go back and refer from the trigonometric identities, whereby from the quotient identity, tan, as we know that tan of theta tan of 4 theta now will be equals to the sine of 4 theta. Now we divide by the cosine of 4 theta. So that is the trigonometrical quotient identity, where now we can apply it to simplify the problem, because here the Moivre theorem only dominated by the cosine and sine, because they are the parts of the real part and imaginary part in polar form of a complex number. So if that to be the case, it means now I need to expand this side. So as later I compare with the real and imaginary parts of this side of the De Moivre theorem, then from there we can work out this sine of 4 theta and cosine of 4 theta. So if that to be the case, now we can say what is needed, expansion of this. So as we can compare with this cosine of 4 theta and the I sine of 4 theta, whereby we can generate the expression for the sine of multiple angle 4 theta and the cosine of 4 theta. So we need to expand this by the concept of binomial, because here we can apply binomial theorem to expand. We have two terms, as the theory states, binomial, two terms. So we can use binomial theorem to expand. Now let's see how we can do it. So now when expanding, that cos of theta plus I sine of theta raised to 4. So here becomes, through binomial, it means it become cos of, then here raised to 4 theta. But this will be power 0. As we go, this decreases, this increases in powers. So we say we plus, it will be the cosine 3 theta, then I sine of theta power 1. Now we plus, this is reduced to the cosine square of theta, then this is I sine of theta, and now because here was power 1, here is power 2 now. So we plus, here become the cosine of theta power 1 times I, the sine of theta now, it will be power 3. Lastly, this cosine of theta will be power 0, that will be 1, cos of theta raised to 0, that is 1. Then here now becomes I sine of theta raised to 4. So we said as we go, this decreases. It started with the highest power, it's the exponent that we have here, 4. But when we go this side, it decreases and this one increases until we reach the highest power, 4. Then we stop. And that's the concept of binomial. Now from there, we need also to know the coefficients of these terms. So through Pascal triangle expansion, the highest exponent here is 4. So we can start by inserting this kind. 1 is, we form triangle here from the Pascal triangle. Now if we add here, we get 2. And once we get the sum, we add 1, 1. Then again, we form another triangles. Then now you add here, you get 3, 3. Then you add 1, 1 after the sum. Then here we form another triangles. So when we add here, we get 4, we get 6, we get 4. Then we add 1, 1. We form another triangles. So Pascal triangle help us to get coefficients of the terms after expansion through binomial. Now this one here stands for when the exponent was 0. Here are the coefficients when the exponent is 1. Here are the coefficients when the exponent is 3. And here are the coefficients when the exponent is what? When the exponent is 4. Yes. And here goes maybe when it is 5. So now we can look from the problem that we have. How many terms do we have? 1, 2, 3, then 4, 5. So maybe here we can say here when the exponent, so we have jumped. So here was 0, 1, then here was 2, then here 3, and here when the exponent was 4. Sorry. So when exponent is 1, we know a plus b raised to 0, we know always we get 1. So when exponent a plus b, when it's 2, we always get the coefficients 1, 1. For example, if you expand this, you will end up getting a squared, you plus c 2ab, you plus c b squared. No more multiplication of taking a plus b times a plus b again. You just end up here. So here you can see coefficients is 1. here is 2, here is 1. You can see the coefficient. But when the power or the exponent is 2. But here for our case, the exponent is 4. It means these now are going to be the what? The coefficients. 1, 4, 64, 1. So we just multiply at the individual terms. Here times 1 has no meaning of write 1 here. So here we just insert 4. Here we also insert 4. And here, no, here is 6 because 4, 6. So here we insert 6. And here we insert now 4, then here we insert 1. So we stop. So here is plus 6. Let me write correctly. Plus 6 here. Yes. So up to that point, now we can proceed. So the expansion now becomes that the cosine of theta plus I sine of theta raised to 4 is less more to what? Now we can categorize them. We can just separate by putting the real part itself and the imaginary part themselves. So we can say we start with the real. Cos raised to 4 of theta. We find all terms that has no I, because the terms without I now will be the what? Or we simplify first. This one becomes 4i cosine cubic of theta, then the sine of theta. But here, remember this exponent 2 goes here and here. When it goes here, it will be I square. But I square, we know is negative 1. So it is going to affect this positive operation here. And it becomes now minus 6 cosine square of theta, then sine square of theta. So if that to be the case, then again, here, cubic. So I cubic is the same as say, I cubic is the same as say, I square times I. So I square is negative, so it gets negative I. So I cubic become negative I. So here now becomes minus 4i, then the cosine of theta, sine of theta, and cubic of theta. Then lastly, I raised to 4, it will be negative 1 times negative 1. That will be positive. Then I disappeared. We remain with sine of sine quartic of theta. Yes. Now from there, we can term separately the imaginary and the real part. So we end up getting cosine of raised to 4, then minus 6, the cosine of square of theta, sine square of theta. Then now we plus the sine of quartic theta. Then we come to imaginary part now, plus I bracket. So we start with this one. Here it is 4 the cosine cubic of theta sine of theta. Then minus 4 the cosine of theta sine cubic of theta, then bracket. So now we have termed separately the real and the imaginary parts for this expansion. But remember now, the cosine of theta plus I sine of theta, complex number in polar form raised to 4, this, according to the Moivre theorem, is less more to the cosine of multiple angle 4 theta plus I sine of 4 theta. So we can just insert here, this one is the same as saying cos of 4 theta plus I sine of 4 theta. Yes, because this is the same as this according to the Moivre theorem. Now, what remains is comparison. We need to compare now to get the sine of 4 theta and the cosine of 4 theta. So starting with the cosine of 4 theta, the real parts. So by equating, so we can say by equating real and the imaginary parts, the imaginary parts of the complex number, then we have, what exactly do we have? Now, what exactly do we have here? So this is going to be compared with the imaginary, because cosine belongs to the real part. So it will be the cosine of 4 theta equals to what? It is the cosine quartic theta minus 6 cos square of theta, the sine square of theta, then we plus sine quartic of theta. Also, the sine of 4 theta is less more to what? To the imaginary part, I sine of theta. It means this I is compared with this expression of imaginary. I and I will cancel out. So we remain with 4 here, the cosine cubic of theta, then sine of theta. Now we minus 4 cosine of theta, then the sine cubic of theta. So this is what now is remaining here. If that to be the case, then now we go for the quotient identity in trigonometry, that tan of 4 theta, the tan of multiple angle, equals to the sine of 4 theta, sine of multiple angle, which is less more to 4 cosine of cubic theta sine of theta. Now you minus 4 cosine of theta sine of cubic theta. Then now here you divide. So here you divide by the cosine of 4 theta, which is this one here. That will be the cosine quartic of theta minus 6 cosine square of theta, the sine square of theta, then we plus sine quartic of theta. So if that to be the case, how do we develop this now expression here, 4 tan of theta? It means now we need to find the power angle of trigonometric function, so as it can act like a device at every term, so as we can simplify. And for the case or the nature of our expressions here, if we divide every term now here by the cos quartic of theta, now will result this expression which is now needed here. So what to do now, let's see how we can proceed. It is too tedious, but you have to be very careful with this trigonometric expansion, but we'll just end up to the right answer. So now this tan of multiple angle 4 theta equals to what? Now we divide every term by the cos quartic. It means this cos quartic, the cosine quartic of theta, this one. If we divide every term, if we divide here, it means down will remain cos of theta. Now sine of theta over that cos of theta will get tan of theta. So where will be now 4 tan of theta? So you'll have 4 tan of theta. Now you minus. If we divide again by the cos quartic of theta here, it means this will remain cos cubic of theta down. And then now when we take sine cubic over cos cubic, we get tan cubic of theta. So we minus 4. So here will be minus 4 tan cubic of theta over. We go down, we divide by the same factor, cos quartic of theta. So if you divide here, we get 1. So here remains 1 minus. Again, if we divide by the cos quartic of theta, so these two goes, will remain 2 cos square of theta down. Now, when we find relation with this sine square of theta, we get tan. So we minus 6 tan square. 6 tan square of theta there. Then now we divide by the cosine quartic of theta. So we end up getting plus tan quartic of theta. So up to that point, I think now they look the same here. So now we have proved that tan of 4 theta is less more to that expression. And here is how now the Moivre theorem has helped us to change these multiple angles into power angles and to look like what it is supposed to be. So up to this point now we can say proved. Yes. So now let's move to another part of this question, part C. Now part C, Roman 1, it's given that we are provided with the equation here, complex number cubic equals to u plus iv. So we are required to show that u over x plus v over y equals to 4 bracket x squared minus y squared. So if that to be the case, for we to solve or to start solving this problem, we need to expand this. So we need to expand this and see how we can develop generating these u over x and v over y to see how we can show this right side. So having said that, now let's see. Okay, see Roman 1, provided x plus iy, the complex number cubic, which is less small to u now plus iv. So we are required to show that one. Required to show u over x with plus v over y equals to 4 x squared minus y, y squared. If that to be the case, we start by expanding this. So we can start by expanding x plus I then cubic to see what exactly we have. And because, very fortunate, here we have two terms, so binomial theorem can work. So we can say now, on expansion of x plus iy, which is less more to say, it is x cubic, then iy raised to 0 with plus. As we go, this for x decreases until it reaches 0. So square now iy, the second term increases this exponent, 1 with plus x power 1, iy now square, then we plus x power 0, then iy cubic. So we stop. And from there, so we can have x cubic. Here will be plus I x square y. Then here, remember here, this 2 goes, exponent 2 goes to I and y. So I square will be -1, so will affect this operator. So the operator become minus. Then xy square. And here, this is 1, because x power 0 is 1. And about here, I cubic is the same as I square times I, which is -I. So here we minus I, then y cubic. Now we come to insert the coefficients. Now from the concept of Pascal triangle, where we can determine the coefficients of the terms from the expanded expression or the series. So now we can start that game of Pascal triangle. So we can say 1, then 1, 1. Now we have a triangle. So we sum, we get 2. After summing, we add 1, 1. Then again, we introduce triangles. So here is when the exponent 0, is when the exponent is 1, the coefficients become this, and when the exponent is 2. But here the exponent was 3, so we still go. We add, we get 3, 3, then we add 1, 1. So triangles. So here is when the exponent 3. So it means now we are going to insert the coefficients of these terms of the expansion. So here, 1 we times here will be x cubic, then 3 we times here will be plus 3 x square y times I. Then now we minus 3 times this, we get 3xy square. And then 1 times this, we minus that I y cubic. And this now will be the expansion for this complex number. So if that to be the case, so we find the environment now. So now we can just insert there and see what we have. So we'll have x cubic with plus 3x square y, then times I. We minus 3x y square, we minus iy cubic is less more to what? To u we plus iv. Yes. So now it's a matter of comparing real parts and imaginary parts. So we just equate from the sides. So here u, this one, is less more to what? all terms without I refer to the real part of that complex numbers. And from here, we compare also IV. Now this will be the star 1. IV now equals to all terms with I, imaginary parts. Minus I, then y cubic. So if we cancel I and I, we remain with V equals to 3x squared y, V minus y cubic. This is star 2. Now from star 1 and 2, we find the possibility of making this. We come to the expression that we are supposed to show. And here maybe we can choose the left-hand side. So we find expression for u over x and v over y from the advantage of these two equations here. So in star 1, if we want to develop u over x, it means here we can factor out x and remain with x squared minus 3y squared. So if we express u over x is less more to x squared minus 3y squared. So now we are lucky that we have u over x that is less more to x squared minus 3y squared. If that to be the case, then now we move for the star 2 to see the possibility of making v over y. We say now also v, which is 3x squared y, then we minus y cubic. If we factor out here y because it's common at every term, now here becomes 3x squared, we minus y squared. So if we divide by y, we end up getting y over v over y equals to 3x squared minus y squared. So from that point, now we have u over x and a v over y. Now on choosing the left-hand side, that considering the left-hand side, where we have u over x, we plus v over y, we need to operate this part here until we get 4 brackets x squared minus y squared. And up to that point, we have shown what we are supposed to show. So from there, we can proceed. So u over x, we put its value, that is x squared, here, minus 3y squared. Now we say, we plus, because here is u over x plus. V over y, it is x squared minus y squared. So from here, operating the like term, x squared plus 3x squared, we get 4x squared. And this much here, we minus 4y squared, because negative 3y squared minus y squared is less more to negative 4y squared. So from here, for we to get this right-hand side here, it means we can factor out the common. The common term there is 4. So this now we take it out. So if we take it out, it divides every term here, it remains x squared minus y squared. So up to that point, now we have shown the right-hand side. And finally, conclusively, we can say u over x, if we plus v over y, is less more to 4 than x squared minus y squared. So here we can say now, hence shown. Hence shown. But the idea was to expand this complex number. Then you compare imaginary parts and the real part. Now you come to formulate u over x from those real parts. You come to formulate v over y from those imaginary parts. And up to that point, we've answered the Roman 1 of part C. Now let's see Roman 2. So case C, Roman 2. Now in Roman 2, if z is a complex number, show that the modulus of z minus 2 over z plus 3i equals to 4 is an equation of a cycle, So here we are provided with the expression z minus 2 over z plus 3i equals to 4. So we need to show that is an equation of a cycle. Now we can let solution Complex number z is always represented as x plus iy. So if that would be the case, now we can say, writing this in the same as say z minus 2, then over the modulus of z plus 3i, then equals to 4. Now, if you multiply both sides by the denominator expression, so we end up getting modulus z minus 2, sorry, here is 2, z minus 2 equals to 4 modulus z plus 3i. Now, from there, put in the value of z as a complex number. So that will be x. Now we join with that to form the real part. Then we plus iy. This is less more to say 4. This now here will be x plus iy. It means we plus I. Then now that 3 we join with that y because they belong to the imaginary part. So that is how it's supposed to be. If that would be the case, now we are going through the concept of modulus. Then we find a way of cancelling out these brackets. It's through the formula of modulus. So if you remember, here will be the radical. Here will be x minus 2 bracket square. Now we plus, it means real part square, we plus imaginary part square. It's less more to 4 the root, square root of x square real part plus the square of imaginary. This way. So on squaring both sides, it means this square root cancel out. And now we are going to have x minus 2 bracket square plus y square equals to, this here will be 4 square bracket, then x square now plus 3 plus y bracket square. So from there, we can expand to see what we have. So if we expand here, we get x square, we minus 4x, then we plus 4. Now we plus y square equals to 16 brackets. Here become x square, we plus, here becomes 9 plus 6y, then we plus y square. So that's how it becomes. Yes. And from there now, we'll have x square minus 4x, we plus 4, we plus y square equals to 16x square. We plus 16 times 9 with the help of scientific calculator. We can just multiply here, 16 times 9. So here we get 54, 5. Then here we get what? 14. So it's 144. So here we get 144. Now we plus 16 times 6. Here we get 36, 3, 9. So it's 96. 96y. Now we plus 16y square. Yes. So that's the terms that we are supposed to get. And from there now we collect the like terms. So we can all take these to the other side. So here, maybe we have 0. Nothing has remained. So 16x square, now we minus this x square, we get 15 x square. Then again, we don't have a term of x. It means now we plus 4x. Then now this 4 goes to the other side. It means we take out 4. So here we remain with the plus 140. So this y square goes. Then now we remain with the 15y square. Because 16y square minus y square, we get 15 y square. So from there, you'll have the standard equation of a cycle like this one. We plus 15y square, we plus 4x. Then for the case of y now, here we have forgotten because here we don't have just y. Yes. And here it means it remains plus 96y. So we plus 96y. Then again, we plus the constant 140 equals to 0. So from there, we have generated the standard equation of a cycle, whereby we can speak of the radius and we can speak here of the center of a cycle. Now, if that is a standard equation of a cycle, now we can say, for example, the center according to the coordinate geometry, the center of a cycle is given by negative g comma negative f. And how to obtain this? We just compare this one with the standard equation of cycle. That 4xc is the same as say 2gx, and 2fy is the same as the term containing y, 96y. So from here, the value of g becomes, this cancel out, becomes 2, and the value of f here, if we divide 96 by 2, when we divide by 2, 4, 8, 116, we get 48. So here we get 48, the value of f. So the center now of a cycle becomes negative g, it means in negative 2, comma, negative f will be negative 48. So this will be the center of a cycle. So when we speak now, we say now, this has represented the equation of the cycle, this one, that one, has represented the equation of a cycle, this one, yes. The equation of a cycle, that's one, with the center negative 2, comma, negative 48. And up to that point, we have shown that has represented the equation of a cycle. And now let's see part D. So part D, if x plus iy, the complex number, is less small to bracket negative 3 minus 2i bracket raised to n, where x and y are the family of real number, and the n is the family of integers. Now we are required to prove that x squared plus y squared equal to 13 raised to n. Now let's see how we can do. Such a part. So now in part D, case D, provided with xc plus iy, which equals to bracket negative 3 minus 2i bracket raised to n. So we are required to use that as a condition now, because if this now prove that, it means that will be our condition. So I'll be the expression or something to start with, so as we can end up getting this. And then now, if you just check clearly, this complex number here is raised to n. So now, it just looks like there is application of the Moivre theorem here. So the way now we can simplify here is like, for example, here x squared plus y squared that you're supposed to show equals to this. It means this can be obtained by finding the modulus of this complex number here. And if this is the same as that, it means the modulus of this part is the same as modulus of that part. So I think the idea is to start with the modulus, calculating modulus on both sides, and now see what we have from this condition, so as we can come and show that part. So if we find the modulus here, as you remember, modulus of a complex number, we just square the real and imaginary part, the square root of the square of real and imaginary. So here, modulus of x plus iy, this one is the same as the modulus of this one raised to n, or which is the same as say, it's a modulus of this complex number, then brackets raised to n. So this and this is the same thing. So it will be the same thing. So from here, because of the idea of the de Moivre, I say this and this will be the same thing, because if we transform to polar form of a complex number, it means this n will get into the angle and making that angle to be multiple. And from there, if you calculate the magnitude while in polar form and the angle in radian measures, you'll end up getting the answer as you calculate the modulus and then you raise to that exponent n. And provided n is known here, is the family of integers. And if that to be the case, now The modulus of this will be x squared with plus y squared, then now the square root, which will be equals to, we find now modulus of this will be negative 3 square with plus imaginary here negative 2 square, then now raised to n. So from there, if we're squaring both sides to kill or to cancel out these square roots, now here remains x squared now plus y squared is less more to what? So here will be 9 now with plus 4, 9 plus 4, but that square is cancelled with this one, so we end up getting here n. We get there n. So from there you can see what we are approaching to what we are supposed to prove. So if we consider now the right hand side to show the left hand side, here we can proceed by saying this will be now 13 raised to n. And from there now you have shown. So you can say here now we have proved. So the idea was to find the modulus. We find if this complex number is the same as this one, it means modulus works. So modulus of this is also the same as modulus of this because the complex number look the same. And from there, we have tried to simplify, and until the end, we have ended getting that x squared plus y squared, which equals to 13 raised to n, provided the n is the family of integers. And now we have proved. And after that point, we are through with that question number 4, appearing in Advanced Mathematics Paper 2 in the year 2024. And thank you very much. Keep watching our sessions.